write down what the rule states, and we'll do it in formula and in words. So first of all, which one's my inside function? They're definitely g of x, and my outside? F of x. And I'm going to label that. So g of x is my inside, and my f of x is my outside. And so here's the derivative formula. We'll say the derivative of f of g of x is the derivative of the outside, leaving the inside alone. And I'll write that down. Derivative of the outside, leaving the inside alone. That's the first part. So you just take the derivative of the outside function, leave the inside function completely alone, you don't touch it, and then you multiply by the derivative of the inside. All right, that's the chain rule. I think we should all verbalize that once together. Because it's helpful when you're trying to remember the rule. If you've said it a whole bunch of times in your mouth, you'll have that muscle memory and it'll walk you through it. So, everyone repeat after me. The derivative of the outside, leaving the inside alone, times the derivative of the outside. I'm sorry, times the derivative of the inside. All right, now let's say the whole thing again. The derivative of the outside, leaving the inside alone, multiplied by the derivative of the inside. Okay, wonderful. So that's it. So let's try an example. We will do my f of g of x is the binomial raised to the 8th power of 3x plus 4. Now looking at that, can you identify an inside function and an outside function? What's the inside function? The 3x plus 4. And what's the outside function? Raising something to the 8th power. I'll even go a step further, and so let's just say I go ahead and label that. That's the inside. And then the whole thing to the 8th, that's the outside. You could even come down here and say that. You could say the inside, like if it helps to diagram it like this, the inside is definitely 3x plus 4, and the outside is something to the 8th. You'll notice I don't bother putting anything in there. I'm just focusing on what the outside function is. The outside function is just something to the 8th. Okay, so now let's try taking the derivative. We will follow the exact rules. Derivative of the outside, leave the inside alone, multiply by the derivative of the inside. So there was my f of g of x, and now we're taking the derivative. So let's write down d dx of f of g of x. And it will become, so what's the derivative of the outside? How do we take the derivative of just the purple part? That we'd like to do. Go ahead, Nada. Yeah, 8. Yeah, leave the inside alone for a second. Just finish taking the derivative of the outside. Yeah, there we go. So there, we just did the derivative of the outside. Right, just do the basic power rule, multiply by 8, subtract 1. Okay, then what? Leave the, yeah, leave the inside alone. So we just did the first part of the chain. Then what do you do? Yeah, multiply by the derivative of the inside. And everybody, it'd be really helpful if you always put that part in parentheses. So whatever the derivative of the inside is, go ahead and put it in parentheses so we're keeping it separate. So the derivative of the 3x plus 4 is simply 3. Because the derivative of 3x is 3 and the derivative of 4 is nothing. So there we go. Now remember, in calculus, everything gets worse before it gets better. This didn't get all that worse. But can we clean that up a little bit and make it look good? Where should we do with the 3? Yeah, we should bring that over and collect it with the 8. So our final answer would be, yeah, 24, 3x plus 4 to the 7. That's it. So that is the derivative. Using the chain rule. Henry. Oh, okay, I like your question. So we have f of g of x is equal to this, then the derivative, you would have to write it like that. The derivative would be f prime of g of x times g prime of x is equal to 24 3x plus 4 to the 7th. That's kind of awful looking. Yeah, and you know what we would do? We would avoid the whole issue together by not even using this notation, and we would just call it function h. You just say, hey, call it h. Because going forward, we're not really going to know what the inside function is and what the outside function is. We're just going to be presented with something, and just by looking at it, we'll say, hey, we'll call that the inside, and we'll call that the outside. It'll be an arbitrary choice that we get to make. And so instead of calling it all of that terribleness, you would just say, now that's h prime of x. Does that answer your question? Yeah, really good question. We won't proceed with keep it on writing it as f of g of x. We'll just do a single function, and we will happen to notice that there is an inside and an outside. Okay, good. Well, there we go. Yes, Chloe. I brought it because the next step was to multiply by the derivative of the inside. And what is the derivative of the inside? The derivative of 3x is just 3. And so that's all that I brought, because the derivative of 4 is nothing. So that's the entire derivative of the inside. Yep. And now, folks, one more thought for you. Notice what, right up here, I said what the inside function was and what the outside function was. If you wanted to, again, you could go ahead and write down right next to it what the derivative is. If this is the function, and this would be the derivative, I could just go ahead and write down that derivative is 3, and this derivative is 8 something to the 7th. Oh, that one first time. Yeah. Now, I don't really know if you want to keep track of your work like this, but it's just a thought that you could go ahead and mentally plan out what's happening to the something to the 8th, that'll become 8 something to the 7th. What's happening to the 3x to the plus 4, it's going to become a 3. And then it's just a matter of using all these parts and pieces to create the answer. Colleen, did that answer your question?
Yeah.
Okay, super. What's that, Rosa? You did like that?
No, I didn't.
Okay, if that's a little bit much, you don't have to do it. By no means do you have to do it. It's more like just planning, like you wanted to plan it out that way. All right, well, folks, let's go ahead and try it. I want us to go ahead and dive in and find, not that first one, let's do a couple functions first, and then we'll go back to the first one. Oh yeah, let's start with number 2. Number 2 is a nice example of a typical chain rule. Yeah, there we go. Okay, so go ahead and write it down in your own handwriting first. It's always a nice practice. And while you're writing it down, do you already identify what the inside function is and what the outside function is? What's the inside function? Yeah, all that bit, right? And what's the outside function? Yeah, 3 something to the 18th. So what I have here then is I have 3 something to the 18th is my outside function, and my inside function is negative. Rapidly running out of markers. Oh, I did. Let's see if this one works. Aha! Negative 8x cubed minus 5x cubed. So there we go. I hope the color coding really helps to make those inside-outside functions pop. So we have an inside function, we have an outside function. Now we can proceed to do the chain rule. Now you notice, to Henry's question, we're not calling this f of g of x. It's just called f of x. Our function is just a function f of x. And that way, when we go to write down the derivative, all you have to do is write f prime. Is that working much better than another way? All right, so let's try it. The verbalization of the chain rule, what's the first verbalization of it? It says, take the derivative of the outside. Okay, that's all I'm going to do. Take the derivative of the outside. So 18 times 3 is 54. All raised to the power of 18 minus 1 is 17. So there's the derivative of the outside. Then what? Leave the inside alone. And then? Times the derivative of the inside. So, and again, put a little dot, put a parenthesis to keep it nice and separate. So the derivative of the inside would be negative 24x squared minus 40x to the 7th. Did I do that right? Okay. All right, well, we did it. That's the chain rule. Nothing needs, what? That's the answer. Nothing needs to be done here. You might be tempted, should we FOIL that together? I mean, first of all, you're like, no, I don't want to. Why would I do that? But can you FOIL that with that? Yeah, you can't do it because there's a 17 right there. This isn't just one binomial being multiplied by another binomial. There's actually 17 copies of this thing, right? All next to each other, and then this little fella at the end. So you cannot just FOIL that with that, and so great, we don't have to. We can just leave it as it is. This is actually the most simplified form. Okay, wonderful. But yeah, crazy to think of all 17 of them sitting there, right? Could you imagine FOILing together 18 different binomials? That would take you the rest of the day. No?
Could you just multiply the 54 by the other function?
Now you could go ahead and sink that coefficient into that one. By all means, you could. So in my opinion, it's fine the way it is, but you certainly could. Yeah, because then it's all together, right? Okay, try the next one, folks. Everyone try it on your own. You've got this function here. Again, if you have different colors, you might enjoy using different colors. I'm going to use a blue for my outside function just to make it more clear. So I've got my outside function to the -3. I've got my inside function to x plus 4. And notice that you have two parts to this question. First, find the derivative using the chain rule. And then second, plug 1 into it and interpret the answer. So take a moment. If you want to chat about it with your neighbor, go for it. If you just want to do it on your own.
Yeah.
Nice. Yeah, really nice use of color. For those of you using color, really nice use of parentheses. Using your parenthesis to show that you're multiplying by the inside, the derivative of the inside. Now you'll notice that this one, once you're done doing the chain rule, you do have a considerable, well, not a considerable amount, but some cleanup to do. There is some simplification that's possible before you go handing this answer off to a client or a friend. So let's go ahead and do the chain rule. I'm saying the chain rule has 3 steps, right? Derivative the outside, leave the inside alone, multiply by the derivative of the inside. So what's the first step? 1?
Find the derivative of the outside. So -3.
Derivative of the outside. Yep. So we'll bring the -3 down and then subtract 1. Did you get -4?
Yeah.
Okay, super. And then JR, next step.
You find the derivative of the inside.
Not yet.
You will be plugging the 2x plus 4.
Right, just leave it alone. Right. Yep. Okay, super. And then Molly, the last part. Okay, perfect, which is just the 2. Okay, so now we have a little bit of cleanup to do. First, we can multiply our coefficients together, and then we have a negative exponent. So how do we write our final answer? Yeah, do the first, do the coefficient first. So 2 times -3 is -6. And then what do we do with the negative exponent? We push it down into the denominator. So now we have 2x plus 4 to the 4 times. That's it. So that's a nice clean answer. That's your derivative. And the last thing they wanted us to do was plug into 1. So now we can actually find f prime of 1. And you can probably do a good chunk of this in your head. So 2 times 1 is 2, 2 plus 4 is 6. 6 to the 4th, I'm not saying you can do it in your head. 6 to the 4th. Is it 1296? Wonderful, thank you. So 1296, and it's -6 over 1296. Now notice something real quick, folks. Remember the subtitle of this course is Advanced Techniques for Algebraic Manipulation and Simplification. If you go ahead and do the whole bottom, and then you have this, then you have to simplify this. And you're like, oh, okay, well, 6 over 1296. And you have to either type it in your calculator as 6 divided by 1296, and then hit math frac, and then, right. So you can do it that way, and then math frac, and it's 1 over 216. Or go back a step. Right here, it was -6 over 6 to the 4th. What can I do right now if I just leave it that way? I can just cancel one of the 6's. So that's just -1 over 6 cubed, which is -1 over 216. So it ends up being the same answer as what I got down here. But probably better to have noticed that that was a 6 over a 6, that I cancel one of them, before I go raising it to the 4th power, making the number bigger, and then having to make it smaller. Okay, well, really nice. So what kind of slope does this thing have? Negative. So that means if you were to make a little graph, okay, a little sketch, what do we know? Then at x equals 1, well, wherever this coordinate is, can we find where that coordinate is? Can I just go ahead and plug 1 into my function to get the y value? So 2 times 1 is 2 plus 4 is 6. 6 to the -3 is 1 over 6 cubed, which is 1 over 216. So apparently the height is 1 2/16, and it's a negative sloping line, and the slope is -1 over 2/16. Well, now that really was a lucky coincidence. It's not very often that the y value is equal to the slope. Plus, it wasn't equal to it. That's positive and that's negative. But I would call this now a little sketch. I don't know what's happening with the rest of the function, but if I just cover it up and I just look right there, I say, oh, that's what's happening right there. I don't know what the rest of the function looks like, but that's what's happening right there. All right. Make that little sketch. I call that a little sketch. Not an etch-a-sketch, just a little sketch. And again, it's like, hey, I don't know what the rest of the function is doing, but right there, that's what's happening right there. Okay, we have a couple more examples of chain rules. Judy, did you want to go ahead and do a chain rule?
No, I didn't.
Not today? Okay, just checking. Yes?
What exactly?
What is what telling us?
Well, so it's a derivative of the f.
Yeah.
So it's not 2 facts.
What,
As a composite, it's 2 facts.
what are you looking at?
Well,
This one?
and if when you do the rule, it's 2 functions, right? Composite function.
It is a composite function. It's a composite function. But what we're really doing is we are just, we're looking at the function, and it's just 2x plus 4 to the -3. We're eliminating from our mind the fact that someone composed two functions together. We're just looking at it. And we're saying, hey, there's an inside part, there's an outside part. I can use the chain rule. Right. Yeah. If you didn't know about the chain rule, you wouldn't be able to take this derivative. So yeah, we're not really thinking about the fact that somebody said, hey, this is f of g of x. We're just noticing that there is an inside, there is an outside, and therefore you can use it. Did I answer your question? I did? Okay. Okay, so let's try the next one, folks. This next one is 5e to the 2x to the 7th minus 2x to the 8th. Do you see an inside function and do you see an outside function? This one's a little challenging. We've never done this with an e function before. It's always easier to look for the inside function. What's the inside function? Yeah, 2x to the 7th minus 2x to the 8th. So the outside must be 5e to the something. So when I write this down, I'll write f of x equals, I'll do my outside function first. It's 5e to the something. And then I write down my inside function is 2x to the 7th minus 2x to the 8th. Okay, so we have an inside function, we have an outside function. To Henry's point, this may or may not have been a function composition. It's just the function we have. Yeah? Okay. All right, so what's the three-part rule? First step, Josh? The derivative of the outside. Everyone, you can always pretend. You can say, well, what if my function was just 5e to the x? Right? Because that's what we're saying the outside function is, 5e to the something. What's the derivative of 5e to the x? Just 5e to the x, right? Because the derivative of e to the x is e to the x, and 5 comes along for the ride. So the derivative of the outside is itself nothing. It's not very interesting. It's still just 5e to the. We just successfully took the derivative of the outside function. It's just not different. It's the same. And then what's the second step? Henry? Henry, what's the second part? Yeah, just leave the inside alone. Yeah, we didn't change anything there either. And then the third step, Rosa? Very good. So that would be what? 14x to the 6 minus 16x to the 7? Oh, no. That's the derivative. You might say, Mr. G, I kind of like this whole chain rule thing because it doesn't seem like we have to do a lot after we're done. Like this one, can we do anything now? No. To Nando's point, we could sink that 5 into there, you know, to move the coefficient over there. We could even move this whole chunk over in front, like if you really wanted to. There's a lot of ways you could rewrite it. I could do 5 times 14 is 70 x to the 6 minus 80 x to the 7 times e to the 2x to the 7 minus 2x to the 8. So is that a valid way to rewrite it? Sure. I'd say there's no right answer to whether or not you want to put the polynomial in front of the e or the e in front of the polynomial.
You multiply the 5 into 20?
I multiplied the 5 into both. Then I distributed the 5. Yeah, because of, you know, commutativity, multiplication, I can write these things in any order I like. So I put the 5 over here in front of the parenthesis, and then I distributed it in. Is that fair? Is that okay? Okay. All right, so that was that one. F of x equals the natural log of x squared plus 4x plus 5. This one's really fun. This is a great example of the chain rule. Because first of all, the natural log function is a function we use all the time in the natural sciences, biology, chemistry, what have you. And the fact that we have an inside function makes it all the more usable in a real-life scenario. So we want to take the derivative of this function. And so, do you see the inside function? X squared plus 4x plus 5. And then the outside function, natural log of something. So I'm going to write down, I'm going to write it that way. Again, you might want to rewrite the function yourself. Take a break in a second here. So my natural log, that's my outside function. And then my inside function is the x squared plus 4x plus 5. Go ahead and try that one. To be fair, this one's a little tricky because you're going to have a fraction. But try it anyway. Go ahead and try to implement this. Do the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. That's perfect. That's perfect. Where is that? Where do you put that? Remember the derivative of the natural log. You have it on your formula sheet here. Where's your formula sheet for that? Is on the previous page. When you do the derivative of natural log, it's 1 over the argument. So that's the argument, so it's got to be 1 over all that. Yeah, so rewrite that so it's a nice big bracket. And on your formula sheet, the derivative of natural log is so the derivative of natural log is 1 over the argument. So it's 1 over the argument, but the ln goes away. The natural log doesn't continue to be a problem. Yeah, there you go. 1 over the argument. Yeah, so natural log has to be 1 over the argument. There's no longer well, I don't know. I mean, you can try to factor it. Yeah, does that factor? I think I agree with you. Sorry. You can't. So this is technically all over 1. Really, but all over 1. Now it's more obvious that x plus 4 can go over there. Oh, not over x squared plus 8. It's over 1. Because you're just rewriting x plus 4 over 1 fractions, because then you can multiply fractions. Okay, let's see what your answers came out to be, folks. So I'll do it right here. So my function, oh, no, I started it right here. I'll just do it where I started it. So the derivative would be the derivative of the outside, which the derivative of natural log, I'm going to write it down again. If you have the natural log, and you want to take the derivative of it, then it's just 1 over the argument. And so the argument is x squared plus 4x plus 5. So it's 1 over the argument, and then times the derivative of the inside. Oh, and notice, I didn't say it. 1 over the argument, and already, just by writing down the argument, did we leave the inside alone? Yeah, by the nature of just putting 1 over itself, that was already leaving the inside alone. I didn't do anything to the argument, I left it alone. I just put 1 over the argument. And then times the derivative of the inside, which is what, 2x plus 4? Why did I write the 2x plus 4 so high up? Yeah, because you know it's going to go into the numerator. Little things like that, you know, sometimes I see people writing down, and it's fine to forget, but sometimes people will put that and then put a big 2x plus 4. And then that can lead to some confusion as to what to do next. Where does that 2x plus 4 go? And so a good rule to think about is that when you have a fraction, everything else should be written as a fraction. So if I'm going to write down 2x plus 4, I might as well write down 2x plus 4 as a fraction. So once you have one fraction in your expression, make everything a fraction. That way it'll be easier to see what to do next, which you just multiply straight across. And did anything factor? Okay, well, folks, I find the derivative of the natural log so remarkable because in the original function is a natural logarithm. I mean, just imagine, it's a logarithm. It's log base e. I mean, log is already tricky enough. E is another tricky thing. And yet, when you take the derivative of it, there is not a trace of a logarithm left. Isn't that amazing? I mean, maybe I'm the only one who thinks that's really interesting. But the logarithm goes away completely. And whereas we started with a logarithm base e, it's now just a rational function. No logs at all. That's really, really interesting. Okay, I think we can take a break. So the time is now 11:54. I'll be back at 12:04. Did you get a chance to go down to the testing center yet? Okay, tomorrow. Okay, super. Now they did close a little early tomorrow. Okay, all right.
As a class to do well.
Yes. You mean as a class of people or as an academic class? So you didn't mean socioeconomic class. I just wanted to make sure I understood you correctly. Yeah, as a class of people.
I thought it was.
Teaching. Actually, I don't think I have anything else to handle with you. Yeah, that's true. And so what meeting I'm hoping? What is it? Well, you know what? I think I actually have to come to campus on Tuesday early for a meeting at 5 a.m. So.
Any meditation? No, I went to work.
Well, you know, do this. I don't know how to do all this food. Okay, I'll send you an email. But for sure, I have to be here Tuesday at 8 a.m. And I don't have class till 11. So we probably do any time between 9 and 11. Okay, I'll send you. Oh, don't give it to me.
I don't want to.
All right, thanks to you for
Do
coming
I
out.
take that home with me?
I sure don't, no. My wife would make me sleep in the other room. She wouldn't make me, I would do it like it.
I think that's worse than my husband said.
Hey, I have a good story for you. I don't think I told you this. So one of my classes, it gets out of like, noon. I went and got my car, drove away. I wanted to go to the room. But it wasn't so bad. It wasn't that person's fault. They got rear-ended, which shoved them in me. Anyway, both got out of the car. It was one of my students who was just in the class that I just left. So there he and I were just doing that. And I was like, okay, class is over. Both got out of the cars, went in the same direction. Somebody hit me. Yeah, I only ever got banged once. Yeah. He, though, because the guy hit him, he actually was attempting to avoid that guy. He went into the bank, hit me, and then went further out in traffic and hit one of the guys. So he got hit 4 times. He had 4 impacts, I should say. Before that. And he's in physical therapy. No, like, that's the field of study.
Oh my gosh.
Yeah.
Now this is on patient.
Yeah, he very much so. Yeah, so that was my first being hit by a student. Fortunately, not with fists.
Yeah, just nice.
Yeah. All right, well, thanks, Jeannie.
I was hoping for a joke I hadn't heard before.
Oh, but you had heard that one? I'll tell you my wife's favorite joke right now. Oh, I'm sure you've heard that one too. I'll tell you this one. Jeannie walks into a lawyer's office, says, hey, how much do you charge? Lawyer says, $100 for 3 questions. He says, gee, it's not steep, isn't it? He says, yeah, what's your third question? Have you heard that one? Yeah. No. Okay. No, no.
See the end of this packet, but are we gonna be doing algorithms where we have to do the chain rule and the product rule?
Yeah, absolutely, that could happen. I mean, what's the most exciting possible problem you can come up with? A chain rule within a quotient rule within a product rule. I mean, just make up a fake example of a problem and see if you can come up with a problem where you have to do all of it. Natural log, e to the x, power rule, product quotient chain. That would be a pretty good function, wouldn't it? Okay, so let's see, what did we just do? 1 through 5. Okay, yeah, then we have a couple more examples. And then those guys. Okay. Well, super. Some of these are kind of duplicate, but there you go. There's one. That's chain and quotient.
Oh, okay.
That's just chain. That's just chain. So we can probably skip some of those because we've already covered it. That's just a chain. Because how do you rewrite the square root? Yeah, something to 1/2. So that's like the one we've already gotten. So yeah, I think that's the worst one on the packet. Okay. But I like the idea of making up a problem that would be like that. And actually, what's the simplest problem that you can create that uses all of them? Because it's easy to make a massive, tricky one, but what's the simplest one that uses them all? Now I'm going to try to write it down. What's the simplest one? I want to use a power function. I want to use an e to the. I want to use a natural. I want to use a product and a quotient. Yeah, I think I have one on that. I feel like no matter what, you need 4 bits to it. 4 different chunks. What were you writing on? I was wondering what that was.
Here, they're velvet.
Deer antler velvet?
I don't know what that means.
Oh, it's a real ingredient. I thought it was just the name.
Was it a one? Let's see. Well, there you go. I think that works. Oh, and you know what? That's nice too, because so you have the product, the quotient, and you have the chain inside the eta. So technically, you just have 1, 2, 3 chunks, and because the x is in the end, it's nice. Mine is on my appendix sheet. I'm only have rock salt too. Oh, yeah. All right, folks, let's continue on with the excitement of the chain rule. Nana and I were just having a fun conversation about what's the worst function ever. They would have a product, quotient, and chain rule, and power rule, and logarithm, and eta that. And so Nando came up with, wait, will you tell me again, Nando, what it was? Log of x. That's e to the x squared. L over x squared. Okay, so does everyone see how fun this function is?
No.
Super fun, right? So do you have the product rule? Yeah, up top, you got the product rule. Do you have a quotient rule? Yeah, over all the top, over the bottom. Do you have an inside function? Yeah, e to the x squared. Do you have a power function? X squared. Do you have a natural logarithm? You have an e to that. Yeah. Does that have everything?
Yes.
It'd be pretty interesting to know what that function looks like. I mean, if you were to graph that, I mean, what do you even think that would look like?
Business.
Yeah, we can check out Des. Should we look and see what that
Does
terrible,
it
terrible?
exist?
What?
Does it exist?
Well, I'm sure it exists. There's an asymptote at x equals 0 because, you know, as soon as x is 0, x squared is 0, and the denominator is 0. Well, other than the asymptote at 0, it could exist. So let's see. That was natural log x times e to the x squared. Right? And then all over x squared. Oh,
That's it.
look at that. Yeah, I mean, that's it. That doesn't even look terrible or anything. It just kind of goes up, and then it goes to the right, and then goes up. And it's almost disappointing, isn't it? So what would the derivative look like? What is the value of the derivative at all times? Positive. So it's just always positive. Now, to tell you the truth, I don't know if there's a way to do the derivative on Desmos.
Use Wolfram.
Yeah, you can use Wolfram. Well, I mean, we can just do the derivative. There it is. It actually did do the derivative. And so it's just a parabola. That seems pretty anticlimactic. But are all the slope values positive, as we thought?
Yes.
Yeah, the y values are all positive. So there you go. And wasn't that neat that I could just type in d over dx? And that told Desmos to do the derivative? Yeah, very fun. Great question. All right. So go back to number 1. Now that we have some experience under our belt, let's take a look again at number 1. Now, number 1, they're getting at the concept behind the chain rule. So take a look. It says, find the following using the table below. So we have a table of values. So first, let's just clarify what this table of values means. So the first row here, f of x, those values, so x, I'm either inputting 1, 2, 3, or 4 for x. And so if I look at this value right here, that's f of x when I input 1. So f of 1 equals 4. Does it make sense? X is 1, I'm plugging 1 into the function, so f of 1 is equal to 4. That 4 right there means f of 1 equals 4. So what is this then? 2. Yeah, f of 2 is equal to 2. So that's what that means. That's how you read the table. What is this then?
1.
F of 3 is equal to 1. Okay, so does everyone see how to read the table? What would this then be? G of x. This would be g of 1 equals 1, or g of 2 equals 4, or g of 3 equals 3, or g of 4 equals 2. Likewise, f prime. So f prime of 1 equals 2, f prime of 2 equals 4, f prime of 3 equals 1. Pretty strange way to display a table. But at the same time, hey, people display data in a lot of different ways. So it's good to expand your experience. So now what are we even asking for? Here's the function h. And again, to Henry's question, it's a composition, f of g of x, but they're just calling it h. Because then we can just refer to h prime. So what we'd like to do then is find h prime and plug a 1 into it. And all we have is the data. So let's start here. Everyone write down h of x equals f of g of x. And so what is h prime? What is the derivative of h? Exactly right, the definition of chain rule. The definition of chain rule is take the derivative of the outside, leave the inside alone, and multiply by the derivative of the inside. So what I just wrote down right there was the definition of the chain rule that we wrote down first. So now we know what h prime is. It's that whole mess. And we're saying let's plug in a 1. So I'm going to write the whole thing empty. H of something, h prime of something equals f prime of g of something times g prime of something. So I wrote the whole thing empty. And what am I going to plug in? 1. So I plug in a 1 here, I plug in a 1 here, and I plug in a 1 here. So now we just go to the table and look up all of this information. What value do you want to look up from the table first? G prime of 1. So G prime of 1 equals 3. So that little part over there is just 3. What can we look up next? The G of 1. So G of 1 equals 1. So now that part is 1, and I still have f prime to solve. So now what's f prime of 1? F prime of 1 is 2. So now that becomes a 2. That's still my 3. And so the answer is 6. Was that an exciting problem? No. Well, did it maybe hurt your brain just a little bit? Maybe. Because it's so unlike anything you've ever done. It's like using language in a new way. Like seeing this whole notion of writing down a very general formula, plugging in a number, and then going to a table. Yep, you found 3 values from the table, didn't you? You found the G prime of 1 from the table, you found G of 1 from the table, and then once you plug that in for 1 here, then you found f prime of 1. And then you just multiply with that 6. Okay, well that was it for number 1. It is an interesting problem. Okay, so where did we get to? We're on 6 now. Here's one just like it, except instead of giving you data in a table, they're giving you a graph. So in number 6, they're saying that f is actually g of x over h of x. That's a comma, not a prime. So f of x is g of x over h of x. I don't even think this is the chain rule, but it's still an interesting problem. So what do they want us to find? F prime of 3. So first we have to find f prime, then we plug in 3. So first let's find f prime, and let's do it in a very general way. If I want to find f prime, and it is a quotient, not a chain. This is the chain. This is the quotient rule. Quotient rule. So how do I write that out? It's O d high minus pi d ho all over O. Last night I was reading this book to my daughter, she's 2.5. It was an elephant, a story about an elephant, and then the elephant was laughing, and the elephant said, ho, 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 ha, 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 ho, ho, ho. And she said, that's what Santa says. And I said, and someday that's what the chain wheel says. Or no, the emotion roll, ho, ho. All right, so there's our function now. That's definitely the derivative of f. So now we just have to plug in 3. So we go back, and we plug in 3 everywhere. So the first thing I'm going to do is write it empty. Right? So empty, h of something times 2 prime of something minus g of something times prime of something all over h of something squared. And we're plugging in 3. 3. So now where do we go look up our values? They didn't give us a table, they gave us graphs. So for instance, what's h of 3? First of all, which graph is h? Yeah, this graph is h. So what's h of 3? That means you go to the 3 is the input, and then the output is that 4.5. Does everyone agree 4.5? And it could be more or less than that, but let's just be friends and assume it's 4.5. Now, I'm going to write this empty again. I'm going to write something something minus something something all over something squared. I'm a huge fan of writing functions empty to just give myself the structure and then plopping in all my numbers. Plopping is the technical term. So h of 3, that was 4.5. So then what's g prime of 3? G prime. So here's our g graph. What does g prime represent? The slope. What's the slope of this graph? Is it 1? Does everyone agree? Up 1, right 1, up 1, right 1, up 1, right 1. Well, there we go. So g prime of 3 is 1. G prime of anything is 1. Right? Because that's just a constant line. I mean, not a constant line. Is it? So here's your g graph. Well, we're wondering what g prime is. G prime represents slope. So what's the slope of this line? Yeah, up 1, right 1, up 1, right 1, up 1, right 1. Okay, then minus g of 3. So now we're back on our g graph and we want g of 3. So we input 3 and the output is also 3. And then we want h prime of 3. Now notice h prime is not just one line. There's a positive slope on the left and a negative slope on the right. So what are we looking for? H prime of 3, we're looking at the negative sloping part of the line. And what is that slope? Negative what? Negative, is it down 1, right 2? Down 1, right 2?
No.
What is the slope?
1.
Is it down 1, right 1? Let's see. If I start here, the middle of that box, and I go down 1, right, and I get to the middle of that box, do you agree that that's down 1, right 1? Is that equivalent to down 1, right 1? It's not landing on a grid point, but it is down 1, right 1. So that slope is negative 1. It is negative 1. Okay, and then finally h of 3. So the h graph, input 3, output still 4.5. Now before we go just diving on plugging all this into our calculator, can we be clever with the 4.5 or no? Can we cancel the 4.5? One of them? We can cancel one of them? Can we really?
No.
No, because that's a minus. It would have had to have had a 4.5 in both. But I only raised it because I thought I could. I got all excited. I was like, boy, I can cancel 4.5. I was like, oh. Okay, so then we just plug it all in. Or just one step at a time. So 4.5 times 1 is 4.5. And then plus 3 all over 4.5 squared is 20.25, which is 7.5 over 20.25, which is something. I got a repeating decimal point 370, 370, 370, so I'll hit math crack, and it reduces to 10/27. So what does that mean? It means if I made a graph of the function g of x over h of x, where I actually knew what those functions were and I actually divided them, and then I looked at the value of 3, then I would know that the slope was 10/27. Can we create this function in a meaningful way right now? I'm not so sure. G of x is definitely just the graph. Oops. g of x is 1x. Does everyone agree that g of x is 1x? It's just a straight line there, x plus b, the slope is 1, the y-intercept is 0, so that's it. And we're interested in 3, so I'm going to come over here and just ignore this part of the graph. What's this line? So far, this is negative 1x, but plus, what's my y-intercept? I don't know. It's up there somewhere, isn't it? Anyone have a guess as to what the actual y-intercept is?
Oh, yeah. There's near the. So,
Maybe around 8? Yeah, maybe 8.5. I suppose we could actually find out, because you can use point slope form, y minus y naught. Oh, the way it is going. Great. And times x minus x naught. And yeah, it is. So I know that the point, I have a point on the graph. I'm just going to use any point on the graph. I'll use the point at the top. So that's 2.5, 5. So y minus 5 equals the slope of negative 1 times x minus 2.5. Am I doing all this right so far? I'm trying to find the equation for the downward sloping line. I don't even care about the upward sloping line because I'm only interested in the value of 3. So now I can go ahead and distribute, and that gives me y equals negative 1x plus 2.5 plus 5. Hey, your guesses were really close. The actual equation was 7.5. Why did you guess 8? That was really close.
I figured 5. Well, the 5 I know is like.
I brought the 5 over, and I here I distributed the negative 1. What did I get 5? Because I chose the point to use as 2.5, 5. I'm using the point 2.5, 5. Sorry, yeah, that was not obvious. I'm using the coordinate that's at the top because that point is on it. So now this is the equation of the line. So what actual function are we looking at then? F of x is equal to g of x over h of x. G of x is 1x over h of x, which I now found is negative 1x plus 7.5. Now, I'm really going overboard here, right? Do I have to be doing this right now? No, we can move on to the next question, but this is interesting. I wonder if we're actually going to get this answer. So now I have to take the derivative of a quotient. So f prime is O d high minus high d ho, right? All over ho. So that's negative x plus 7.5. So my numerator now is negative x plus 7.5 plus x. And look at that, my x's cancel out. So my answer is 7.5 over negative x plus 7.5 squared. Now what number am I plugging in? 3. So negative 3 plus 7.5 is 4.5 squared. That is the answer. It actually did agree. 7.5 divided by 4.5 squared did come out to be the answer we expected. Okay, well, I mean, is that cool? Are you impressed? It really worked out? It really worked out. It really was correct. I thought that was interesting.
When we don't all of that, right?
Yeah, all you had to do was just this part.
Oh.
Yeah, but it's just kind of neat to know that you could always come up with an equation for what a graph represents and then actually do the derivative and then confirm the answer. You know, if you think that's cool. All right, so where are we at now? Then number 7. Number 7 is another conceptual problem where they don't give us everything. They don't tell us all the information. They say, given that f of x is equal to x to the 10 times another function, h of x, and they don't even tell us what h of x is. And see, a problem like this is designed to kind of hurt your brain a little bit, to be like, I don't know all my information. I don't know what h of x is. But we're just kind of holding that at arm's length, saying, let's do the calculation anyway. Right? So everyone write down in your own handwriting, f of x equals x to the 10 times h of x. By the way, what rule are we using now? Product, quotient, chain. So this would be a product rule. So if I did want to find, now notice they're saying calculate f prime of negative 1. So we have to find f prime, and then we have to plug negative 1 into it. So what is f prime? It's the product rule. And we'll write it down as the product rule. Derivative of the first, go ahead, Rosa. The next to the, right? Derivative of the first times the second, plus derivative of the second, which you simply write down h prime of x. Because that is the derivative of h of x, it's just h prime of x, times the first. So that's f prime of x. It might not be very satisfying because we don't know what h is. But again, you're just saying, hey, I don't know what h is, but this is still the right answer. So then we write an empty, find something equals 10 something to the 9th, h of something plus h prime of something times something. 10. Wow, that's a lot of empty parentheses, isn't it? I can see why somebody might say, Mr. G, that's more confusing. Don't do it that way. But see, I still am a believer. I'm a believer in writing it empty and then just going through and plugging in all my numbers. So now what number am I plugging in? -1. So -1 there, -1, -1, -1, -1. Now a lot of this simplifies pretty easily. Like what's -1 to the 9th? No? -9. No, -1. Yeah. Because a -1 times itself an even number of times is positive, but times itself an odd number of times is negative. So that just gives us -10. And then I have h of -1, which I don't know what that is yet, plus h prime of -1, which I don't know what that is yet. Well, that's true, we do. I just haven't done it. I'm just taking care of the ones first. And then -1 to the 10th is? -1 to the power of 10 is +1, so I'm not even going to write it down. This is +1 multiplying something times 1 times 1 doesn't matter. Okay, so now, yeah, we do know what those values are. Yes?
So what did you do to the power of 9?
What did I do to the power of 9? I did -1 times itself 9 times, which is -1. And then -1 times 10.
And then, oh,
Yeah, good question. Okay, so now, yes, we do know h of -1 is 5. And h prime of -1 is 8. And I'd just like to point out, now that we're on this line, it gets worse, and then it gets better. But I mean, look at the last line of this calculus problem. It's laughable. It's arithmetic. You multiply and then you add. It's almost insulting. That like the end of a calculus problem should be so easy. Because you're like, man, I did all this work, and then in the end, I'm adding -50 plus 8. Really, it does almost feel insulting. Like you want it to be hard the whole way. All right, how is everyone feeling about all this? Right, go ahead.
So before the third step down.
Yep.
Okay. Oh, yeah, okay. That one, the last one, the H. -1.
Yeah.
You take all the -1 and you put the right.
Yeah, because that's what they tell us it is.
Okay.
Yeah. All right. Well. Okay. So some of these problems, I'm going to do one of these square root problems with you, but not both. And then I think the next couple of problems we've already basically covered, so we can just cross those out. So let's do a square root problem. Notice now that we've done quite a few different chain rules. We've done a chain rule where you have an inside function and a power function. We did a chain rule inside of an eta. We did a chain rule inside of a natural logarithm. So now we're going to do a chain rule inside of a square root. And really, if you look at this, I just wrote down 4 different ways to make an outside function. Right? These are all ways to do an outside function. And then you just plug something in for the inside function. So we're now about to do another chain rule. You have the obvious inside function, the x squared plus 3x plus 7. And the obvious outside function, which is the big square root. So, first of all, are we going to keep the square root? No. Instead, we're just going to write what? Yeah, we're going to put all that in parentheses and do the 1. And then the inside function is 2x squared plus 3x plus 7. What's that? We're about to do the derivative. Yeah, what I did so far was I just rewrote the square root as a power of 1/2. Because by definition, a square root is raising something to the power of 1/2. Okay, so now the chain rule. First step. Derivative of the outside, so bring down the 1/2. Subtract 1, which is subtract 2/2, which is now -1/2. Leave the inside alone. 2x squared plus 7. And then, yeah, so do what? 4x plus 3? We'll do that correct? Take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. Okay, some cleanup to do. What does the negative exponent tell us to do? Push it down into the denominator. Notice we already have a fraction. So watch what I'm going to do here. I'm going to use my first fraction, 1/2, as my setup for the fact that I know that I'm going to have a fraction. Because this thing has to go down to the bottom. This thing is in the numerator. And my 1/2, I have a 1 up top and a 2 in the bottom. So I'm going to use my 1/2 as a setup for the entire fraction I'm about to make. So where do I put the parenthetical to the negative 1/2? In the denominator. So that becomes 2x squared plus 3x plus 7, the 1/2. And where do I put the 4x plus 3? The numerator. You can remind yourself of that by putting it over 1. So indeed, the 4x plus 3 goes in the numerator. So far I have that. Do I really need the 1? No. I just get rid of the 1. And then what do I want to rewrite my 1/2? That's the square root. So what I really have is 4x plus 3 over the square root of 2x squared plus 3x plus 7. That's it. That's a nice, clean answer.
So 3 comes with 4, right?
Uh-huh. Right, so now we get to plug in 4, because we're at common 4. Yeah.
What's inside the parentheses is called
I don't recall what I just said. Did I call this the parenthetical? Yeah, I'm referring to that big old parentheses. That's what I said. And if I say it, enough other people say it, it comes a thing. Yeah, the parenthetical. Yeah, I'm pretty sure I heard that. Okay, so yes, now let's find f. Oh, I dropped my prime. Let's find f prime of 4. Now, what is finding f prime of 4? A whole bunch of arithmetic. So it's going to be 4 times something plus 3. And then 2 root 2 something squared plus 3 something plus 7. And then in all of that, I'm putting in 4. Now, I know a lot of people might potentially just want to take and like type all of that into their calculator all at once. And then you just keep typing and typing and typing, and then you hit enter and you pray. But I think the safer bet is to just start calculating it all in your head. So like 4 times 4 is 16 plus 3 is 19. And then I have 2 times some square root. What's in the square root? Well, 4 times 4 is 16 times 2 is 32. And then 3 times 4 is 12. And then plus a 7. I really trust the baby stepping process. If you want to type it all in your calculator, go for it. So then that's 2 times the square root of 44 plus 7 is 51. That was pretty done. What might we do? We might calculate a decimal approximation so that we could actually give a verbalization of the slope. Because nobody would say, up 19, right, 2 root 51. You'd only say that to an enemy, not a friend. So instead, you'd say 19 divided by 2 root 51. And that turns out to be 1.33. So you can say, up 1.33, right 1. That sounds a whole lot better. You know, if you were speaking to a friend, you're saying up 1 and a bit, right 1. Up 1 and a bit, right 1. You can really visualize that on the graph.
How do you do the calculator to get the 1?
Whenever you do a fraction in your calculator, I would wrap the whole numerator in parentheses, the whole denominator in parentheses. Because otherwise your calculator might misunderstand what you're dividing by. But that's how I typed it in. If you want to see it, I typed in 19 divided by parentheses 2 root parentheses 51 parentheses parentheses. All right. So I'm going to leave number 9 for you because it's exactly like the problem we just did. And if you turn the page, number 10 is exactly like the problem that we already did. And number 11 is exactly like the problem that we already did. So those are all really good practice for you. And you'll have problems like that on the online homework and more. So let's look at a slightly trickier one, number 12. And plus, we still want to have time to look at these word problems at the end. All right. So this, number 12, is a little bit like what Nando and I were talking about, like a terrible function. Because what 2 rules do you have to apply? And, well, yes, it is a power, but more specifically, you have an inside function and a chain rule. So we have a quotient and a chain. Talk about exciting. I'll just leave that up there and I'll work down here. So that begs a really interesting question. What do we do first? I have one vote for quotient, and I have one vote for chain. What do we do first? No. What do we do first? Let's think about what the quotient rule states. Because you can reason this out in terms of what should be done first. When you have a quotient rule, what you're looking at is something over something. Because then you have your ho, you got your high, and ho. And that's all you're looking at. And that's how you implement the quotient rule. Is that what we're looking at? No. So we can't implement the quotient rule right now. Because this is not solely what we're looking at. We're looking at something embedded within something else. And so the idea here is that as soon as you see an inside function and an outside function, you have to do the chain rule first. You have to. Now, and look what happens when you do the chain rule. We have our outside function, our inside function. I'm going to read this one in blue. So I've got my outside function and my inside, and the chain rule walks you through the process. It tells you exactly what to do. So chain rule says derivative of the outside. And look at the very first thing you get to do. Well, after you do the derivative of the outside, you just leave the quotient alone. You do nothing to it. Isn't that wonderful? The first thing you do to the quotient is nothing. Just leave it there. But then you have to multiply by the derivative of the inside. And you'll notice I put a big bracket there. Because what do we now do? Now we do the quotient rule. So we set ourselves up for this nice big quotient rule. O d high minus I, big enough. D O all over O. Chain rule part wasn't all that bad. Okay, so O d high. What's the derivative of x plus 1? Yeah, just 1. Because derivative of 1x is just 1. Derivative of 1 goes away. So O d high minus high. D ho, derivative of the bottom is still 1. Over O. So now we have 5, the quotient to the 4th, and over here we have, that's just x plus 2. Well, did I get rid of all these parentheses now in my numerator? Because that's just being multiplied by 1, so the 1 doesn't matter. That's just being multiplied by 1, so the 1 doesn't matter. So we really just have x plus 2, and then minus the x, minus the 1, minus the x, minus the 1. All over x plus 2 squared. So what wonderful thing happens in the numerator? You get to cancel those x's, which we've really come to expect, right? Lots of cancellation in calculus. And so what do we really just have? 1 over x plus 2 squared. How does it look? Did we do anything else?
That's good. No, that's good.
What about it? Oh, if you wanted to, you can FOIL it. I don't think that'd be our best bet right now. You can't. A lot of things you can do. It doesn't mean it would be more simple if you did. But look at our denominators. They're actually the same. Now we're multiplying. Notice what we're about to do. This is part of your advanced techniques for algebraic simplification and manipulation. So when you have a fraction to a power, you can rewrite it as the numerator to the power times over the denominator to the power. So I can just go ahead and say numerator to the 4th, denominator to the 4th, and then I have over here x plus 2 to the squared. And so now what can I do with my denominators? Yeah, you add the exponents, you multiply them together, you add the exponents. So we can now merge everything, and by the way, where can the 5 go? The 5 would go in the numerator. So our final answer would be 5, x plus 1 to the 4th, all over x plus 2 to the 6th. And boy, that looks really nice. That looks nicer than where we were when we stopped the chain rule. Because now we got to merge the denominators together, shove that 5 up into the numerator, and now we have a really nice clean answer. And now I'm having a hard time getting the word aesthetic out of my head. Aesthetic. Do any of you use the word aesthetic? I mean, if you're fields of study or professions? What does aesthetic mean? What hobby is that? What does aesthetic mean? The way something looks. There's a one-word synonym for aesthetic that's a little better. Word. Oh, appeasing. I like it. What? Oh yeah, appearance, appeasing. A lot of people might redefine it as beauty, or even better, beauty, or even better, elegance. All right. So as I'm up here, I think about all of you. What are they experiencing? What are they thinking? What are they feeling? Are they disgusted by this? Are they okay by this? And like I can see how like going from here to here, you could have this lingering question in the back of your head going, wow. Like that was fine, you know? Do the derivative of the outside, leave the inside alone, multiply by the derivative of the inside, boom, I did it. But then we keep going. Right? And that's because of this thought of aesthetic and elegance and beauty and what makes an answer clean and crisp and good looking. And I feel bad. I should have a better justification for you as to why we do some of the algebraic maneuvers that we do in this class, but ultimately it is for elegance. It is for aesthetic. It is for making your answer look as good as possible. And I think we all agree that answer is gooder than that answer. Yeah, it's gooder. It's more aesthetically pleasing. It looks better. All right, let's keep going. The other thing I was going to think is you might then be left feeling a little anxious going forward, like, well, how do I know when I'm done? Like, am I done now? Am I done now? Like, is there something else I should be doing? And that's a really good question. I mean, the important thing is that you ask the question. You know, if you at least ask the question, like, is there anything else I could do to this? Because then over time, you just develop more experience and you have more thoughts. Like, you know what I can do to make this look better? That'll look better. Okay, so what do we have? We have some more problems now. Video drives. After all, this is a business class. Let's apply some business questions to all of this. Anyone have any thoughts or questions you want to say before we move on? Henry? Oh, I thought you had a hand on.
It's kind of it's like, how do the graphs relate to each other?
How do the graphs relate to each other? The graphs.
Yeah, like the two functions that make one.
The inside and the outside?
Yeah.
Oh, that's interesting. You're saying how do they relate to each other?
Like in terms of like
Maybe. It's an interesting idea. Let's look at one. So for instance, didn't we just do a quotient rule? We did. We had x1 over x plus 2 and then something to the fifth. So let's attempt to look at this question that Henry just asked. So on the one hand, we have the function x to the fifth. Do you all agree that's the outside function? Okay, so there's the outside function. On the other hand, we have an inside function, which is x plus 1 over x plus 2. So ignoring x to the fifth for a moment, there's our inside function. So we have an inside function, there's our outside function. What does it even mean to plug the inside function into the outside function? The result would be x plus 1 over plus 2 raised to the fifth. Is that what we thought? I mean, that's definitely funky right there. Look at that. It's just kind of like, and then stays down for a little bit, and then it starts going up again. So, Henry, I don't know if I'm approaching your question. There's your outside function, and then there's your inside function. And then if you shove the inside function into the outside function, you get that. Is that what you're asking?
yeah, well, it's like it wants demand.
Yeah, how do they relate to each other? I don't know that there's one specific question, Henry. It's a fun question. Keep rolling it around in your head, and maybe we'll get to a problem where you're like, boom, that's it. That's the answer I was looking for. Okay. All right. So suppose a product's revenue function is given by that, where R of Q is in dollars and Q is in units sold. Let's take a minute and look at that revenue function. So, like that. So suppose a product's revenue function is given by that. So we have R of Q equals negative 8q squared plus 700. So first of all, what does that graph look like? First of all, what's my revenue at $0, or revenue at 0 products? 0, right? So I know that my graph goes to the origin. And furthermore, what is the shape of my graph? It's an upside down parabola. So I have a pretty good idea about what I'm looking at. And so revenue apparently goes up, and then eventually revenue comes down. So it's interesting that somehow the more overall products you sell, your revenue decreases. Don't know how that works. Don't know why that would make any sense. Because if I keep selling more and more and more pizzas, I don't know how my overall revenue is eventually going to come back down to nothing. Does that make sense to anybody?
No.
I'm not sure either. But maybe it's not for us to know. So, but that is it anyway. And furthermore, remember, what is the formula for revenue? That's always PQ. And you'll notice in that function, can I factor out a Q? Yeah, so in fact, I could rewrite this now. I'm going to say it's actually Q times P. That's for sure revenue. And so what I have here, if I factor out that Q, I've got negative 8Q plus 700. So now what does that tell me this thing is? Is that my price? It has to be, because revenue is price times quantity. If I factor out a Q, then that has to be my price. And thus, this is my demand function. Now, do we really have to look at all that and know what all that means? No. I just, just kind of looking at what information we're given and trying to wrap our mind around everything that we possibly know in this situation. So we're saying that this is our revenue function, which we know is price times quantity, and therefore we also now know our demand function. Do we need that? I don't know. We haven't even finished reading the problem. But this is a good practice to just get to know your word problem, like you get to know somebody on a first date. Okay, so, and furthermore, RFQ is in dollars. So this is straight up dollars, not hundreds of dollars. And Q is units sold, not tens of units or hundreds of units, just units. So find a numerical value for the marginal revenue at 16 units and record your results in the box below. Okay, wonderful. So marginal revenue. One of the questions on the test, which I didn't count towards or against anybody. The very last question was about marginal revenue. It's taken in 2 different ways. And after grading everyone's test, I realized we didn't spend a lot of time talking about that. So I just didn't grade that particular question. But there were 2 answers, right? So everybody, let's write this down together. You have a pre-calc way of doing marginal revenue, and you have a calculus way of doing marginal revenue. The pre-calc way is actually finding the revenue for 16 units minus the revenue of 15 units. And that's going to actually find the marginal revenue at the 16th unit. So what we're really saying is, how much revenue did I get from the 16th unit? That's what marginal means, that one in particular. So if I want the marginal revenue of the 16th unit, I'll even put the TH. So we all know we're talking about the revenue from that unit. It's the revenue from all 16 minus the revenue of the first 15, and that's going to be the actual revenue that I got from the 16th unit. So now we have to do some arithmetic. All right, we're going to do a little arithmetic. We plug 16 in, plug 15 in, so let's see if we can do this. Negative 8, 16 squared plus 716. That gives me 9152 minus, and then plugging in 15 instead. Gave me 8700. And subtracting 2, I got 452. So $452 is the actual revenue that I got from the 16th unit. This is the exact answer. That's actually how much revenue I got from the 16th unit. I plugged it into the revenue function. Yeah, into the revenue. Because we're asking for marginal revenue, so you have to use the revenue function. Yeah. Okay, so that's the actual answer. Whereas marginal revenue is implying how much revenue did I get from that item. I could actually go to the 16th item and look at that point and calculate the slope. Why would the slope give me that answer? Slope is the change in revenue over the change in how many items do you have. And so the units for this would be whatever that slope is. So you calculate your slope, you put it over 1, and you're saying That's that many dollars of revenue per 1 unit. Which unit? The 16th unit. So now the calculus way means you just find the derivative and plug in 16. Because the slope at 16 is telling you dollars per that 1 unit that you just did. So if we take the derivative, so r prime q is actually negative 16q plus 700. And so, now I can plug in 16. So that's negative 256 plus 700, which is 444. Did I get the same answer? No. And that's because this is just an approximate answer. Now, this is a little counterintuitive. You say to yourself, which way gives me the exact marginal revenue? The non-calculus way. You think, oh, the calculus is so fancy. Calculus will give me a better answer. No. This is the actual definition of marginal revenue. This is the actual definition. This is an approximation. And the reason you'd even do this approximation is that it's actually easier to calculate. This calculation is easier because all you do is take the derivative and plug in a number. Over here, you have to do 2 full-on different calculations with a complicated formula, whereas by taking the derivative, you get an easier formula, and all you have to do is plug in 1 number. So this calculation is easy, and the trade-off for getting to do an easier problem is that your answer is not as good. And anytime you cut corners, the result is not going to be as good. So we cut corners, we did an easier route, but this is now approximate. Okay, so that's the 2 different ways to get marginal anything. You could have done this with marginal cost, marginal profit, marginal revenue. So we just want to remember now, this is the definition of the pre-calculus method. That's the exact answer. And this is the calculus method, which is approximate. Class is over. I always wish we could stay. So where does that leave us? We did 13. There was 14 and 15. So there were only 2 more problems. So please go into more and do as many of the homework problems as you can up until the last 2. And then on Tuesday, we'll come back and we'll finish those last 2 before moving on. Hey, if you have any questions, come see me. I have office hours right now. You're always welcome to come on up. If you just want to come up and talk about calculus, yo. One, I need to see all of your packets. And Rosa, you said you drop them off tomorrow?
Yeah.
Okay, that's fine. It wasn't 3 tomorrow. Okay, so you want to give yourself at least 2 hours. Everybody in the room got 2 hours. So you shouldn't only give yourself an hour because then you'd really be rushing. But